Hello, I am Ali Sadr, a PhD student at the University of Toronto. Today I'm going to show you how to do a couple of basic simulations using free LTSpice software circuit simulator. You can download this software from Analog Devices website. There you can also find the different tutorial documents and videos. The installation process is very straightforward. You may also consider this website for more details on different types of simulations. Of course, you can find various tutorial videos available online. The goal of my video, though, is to simply go through some basics and the process of adding or importing component models. Okay, let's get started. All right, here is the LTSpice environment. You can create a new schematic by clicking on File and New Schematic. Once you've got a new schematic page, you can start to place and route different components. Before that, let me quickly mention some of the main shortcuts here on the top menu. So here you have the most frequently used component shortcuts such as resistor, capacitor, inductor, and diode symbols. And here you've got the ground of your circuit, which is necessary to set the reference voltage of any circuit. You use this pencil symbol for wiring or interconnecting circuit elements. And here you can label different nodes or wires. You have also this shortcut to select your more advanced components where you can have access to various libraries, namely analog devices and linear technology components, such as different op-amps, transistors, regulators, diodes, voltage and current sources. Okay, let's begin by setting up different simulations for a very basic, simple RC circuit. To do so, what I need is to place a resistor. You can press Ctrl+R to rotate it. A capacitor and a voltage source. The next step is to do wiring. Don't forget to place the ground of your circuit. Now the circuit is built and completed. You can right-click on each element to set different values and properties. I choose this resistor to be 100K, this capacitor 100 nanofarads, and I'm going to select the type of the source as a 1 volt DC source. Next, we can label the desired nodes. I can hit this shortcut. I can write my node name, VN. I can place it right here, and same for the output node. Okay. So it's time to go and perform different simulations. First, I'd like to do DC operating point simulation, where you can see the steady state DC voltages of different nodes and DC currents of different branches. To do so, click on Simulate and hit Edit Simulation command. Here you can see different type of analysis and simulations. I choose DC operating point, okay, and I place it somewhere on the schematic. Now the circuit is ready to be simulated. Again, you go to this part, simulate, and press run. Here you see a report document where you can see different voltages and currents in a steady state. For example, the value of the output voltage is 1 volt, which makes sense because in steady state the capacitor is open. There is no current flowing through the resistor, so the voltage drop across it is 0. The output voltage would be equal to the input voltage. The value of the current is 0. Moving on to a different analysis, we can perform a time domain or transient simulation, which is essentially solving the voltage and current of different nodes in branches for specified time steps. Let's first change the type of the input source to generate a square wave that swings from 0 to 1 volt with a period of 200 milliseconds. To change the function, right-click on the source and hit Advanced button. Here you can see different functions. Let's choose a pulse signal. And here you can set values of the parameters. To clarify the parameters, take a look at this picture. Here, V initial and V on are the pulse low and high voltage values. T delay is the time until the pulse waveform begins. T rise is the pulse rise time, here defined as the time it takes for the voltage to change from V initial to V on. And T on is the time that the pulse is at voltage V on. T fall is the pulse fall time, and T period is the period of the waveform. Okay, let's assign the values we want for the parameters. I assign 0 to V initial and 1 to V on, 0 to T delay, 1 millisecond to T rise, same for fall time, T on 98 milliseconds, T period 200 milliseconds, and we set the number of cycles to be 2. Okay, click on OK. And here, what you need to do is to change the simulation type. You can right-click on the simulation, and because this time we want to choose the transient simulation, we need to go to Transient tab, assign 400 milliseconds to the stop time, because we had 2 cycles, 0 to the second parameter, since we want to catch and have the information from 0 second, and the maximum time step to a reasonable value, say 100, and click on OK. So here the circuit is ready to be simulated. Click on Simulate and press Run. Here you can see a blank graph. To add different waveforms, you can either put a prop on different nodes, or alternatively, you can right-click and select Add Traces and choose your waveform of interest. Here, for simplicity, we go with the first method. So I'm going to see the output and input waveforms on the same graph, and here you go. So to measure the voltage and corresponding time, you can click on the label, and you see that a cursor shows up, which can be moved to your desired point. So on this panel, you can see the values. And so for example, here, I'm going to find the time constant of this RC circuit. which is the time at which the capacitor voltage reaches 69% of its final value. Here it's about 10, 12 milliseconds, which makes sense if you multiply the value of your resistor R by your capacitor C, you get 100K times 100 nanofarads, which is around 10 milliseconds. So you may see the reason we chose those values for the pulse parameters, as we wanted the capacitor to have enough time to reach its final value. All right, another thing I want to add is the layout of the waveform. You can set the color of the background, traces, grids, and everything by changing the control panel setting. You can click on this icon and go to the waveform tab and then hit the color scheme and click on different parts that you want to change. So for instance, I'm gonna change the background color to white. So I have to change R, G, and B values to 255 and click on OK. Now you can see that the color has changed to white. So yeah, now we can do other type of simulations. Let's close the graph window and change the input source to a sinusoid. Again, right click on the voltage source and this time choose the sine function. You need to assign values to different variables. DC offset is 0, which is fine. Amplitude is 1, which is okay. Here I'm assigning 1 kilohertz to the frequency. I'll enter 0 to the next 3 variables. And let the number of cycles to be 400. Okay, click on OK to close this window. So the simulation setup is fine. Rerun the simulation to see the resulting waveforms. For this sinusoid input, if you want to see the output voltage, again, you have to probe this node. Then you can see the plot of the output waveform. As you see, to reach the steady state condition, you need to give the circuit enough time. From 0 to about 40 milliseconds or even less, you have the transient condition. But from this point on, then you have the steady state response. So if you want to zoom in here, you can clearly see the amplitude of the signal, and you can also measure it. So again, you can click on the label and move the cursor. So you can measure the peak value, which is about 14.7 millivolt. If you want to measure the relative phase, you need to probe your input and measure the phase of the input and the output at the same point and measure the difference. Okay, sounds good. So let's close this window. Okay, the next topic is the AC simulation. The AC simulation performs the circuit analysis in the frequency domain. In other words, your variable is the frequency as opposed to time in the transient simulation. The response of the circuit to different frequencies are calculated and plotted. Here we want to see the frequency response of this RC circuit. We know that this circuit acts as a low-pass filter where the low frequency signals can pass through the circuit and reach the output, while the low frequency signals can't. Let's first change the input source to be compatible with this type of simulation. Again, right click on the source and change the function to none. Then on the right side, give 1 to the AC amplitude. You don't need to enter anything in the AC phase. Hit OK to go back to the schematic. The simulation type has to be changed to the AC analysis. Right click and go to the AC analysis tab. First, we need to define the type of sweep. Usually we prefer the decade sweep to capture a long range of frequencies with a meaningful and observable change in the response. Next, we need to assign a reasonable number of points per decade. Here I enter 100. The start frequency is already set to a small value, so we can see the low frequency response of the circuit. The stop frequency should be chosen based on your desired range of frequency, and normally we want to capture a good portion of the response. I choose here 1 meg because I know that the time constant of the circuit is 10 milliseconds, so 1 over this value times 2 pi gives me about 16 hertz. So the stop frequency is a few decades higher than this value. Click on OK and run the simulation. Probing the output waveform, you see this graph, which contains both amplitude and the phase response. You can click on the label to measure the values you want. As you see, the plot looks like a low-pass filter. The magnitude starts off from 0 dB and gradually rolls off by the frequency. Based on what we discussed earlier, the 3 dB frequency must be somewhere around 16 hertz. Let me see if the measurement can if the measurement confirms that. Here you go. So negative 3 dB, and the frequency at that point is 16 hertz. So also at that frequency, you should have negative 45 degrees for your phase, which is correct. All right, next thing I'm going to discuss is importing element models that are not already available in the LTSpice libraries. You can find SPICE model files of different components such as op-amps, discrete or integrated transistors, and diodes from different vendors' website. So here I just want to simply download and add the model of 741 op-amp. If you look at the libraries, let me just make a new schematic. And if I go to the component and go to the op-amp parts, you cannot find a model file of 741 op-amp. So what you need to do is to Google it and find it on the web. I have Googled it here, 741 SPICE model, and I found it on Texas Instrument website. If you go to this website, you can simply download it and save it somewhere in your hard drive. If I go to the location and extract the file, you have this text file, and if you open it, you will see different parts. On the top, there are some descriptions, and here in the middle, you have the definition of your sub-circuit. And here is the name of the component, and these are the pin names. And on the bottom, you can see the details of the netlist. Okay, so the next step is to draw the schematic of your circuit with a generic op-amp symbol and then add this model. So the generic op-amp symbol can be found in the component libraries and under the op-amp category. Let me go inside this category, and here it is, op-amp 2. Click on OK. You can see the description. Click on OK and then paste it somewhere in the schematic. Okay. So let me add other components. I just want to make a very simple non-inverting configuration. I need to add 2 resistors, R1, R2. Let me just do wiring. I need to connect 2 resistors and also connect it to the op-amp. So I need to add the input source. Here simply I'll go with a DC source. I need to also add the supply voltages. I need the positive and negative DC sources. So I will rotate V3 to make sure that I'm connecting the negative voltage to the negative terminal. I do the rest of the wiring. Okay, so please note that these 2 wires are crossed over each other and they're not connected. Don't forget to place ground of different nodes. I need 1 ground there, another ground here, and another one here. I need to also ground the 1 terminal of this resistor. So the circuit is completed. I need to assign different values to different components. If I want to have a gain of 10, I need to assign 9K to R1 and 1K to R2. So the gain, the value of the gain for this configuration is 1 plus R1 over R2. I'll set the DC value at the input source to 1 volt. And I also assign 15 volt, a typical voltage for this op-amp as the power supply levels. I need to do also for the negative voltage. Click on OK. Now the circuit is ready to be simulated. Before that, let me just add labels. So here N is there, and I need also to add the output label. I'm just placing it right at the output node. So yeah, the circuit is ready to be simulated. I need to define the simulation type. So I click on simulate and go to edit simulation command. Here, for simplicity, I choose a transient simulation. For instance, I can assign 1 milli to stop time and set the second parameter 0 to 0 and the maximum time step to 100. You can just place it somewhere in the schematic. Then, yeah, so the circuit is ready, but before that, we need to define the component attribute of this op-amp. So I need to change the value of this op-amp to the name of the model file. So lm741/ns. I just copy it and paste it here. So click on OK. Now you need to somehow define and introduce the netlist. Click on Spice directive, and you need to copy paste the content of the file. So you can copy all the content and paste it right here. Click on OK and paste it on the schematic. So here you see again the content of the file. Now let's simulate it. Yeah. So here is the blank waveform. Let me just close the previous schematic. So you can just prop the output voltage, and here you go. You can see the output voltage, and if you note, you have 10 volts at the output. So 10 times the input voltage, which was 1 volt. So the circuit is working correctly. So of course, there are other ways to add the model. For example, you can save the file and use .include or .leave in your SPICE directive. Even you may make a symbol out of your op-amp and assign the model file to the symbol. Then you can add it to your library, like what we've done for the regular elements available in the library. So if you want to know more about this, you can find huge source of videos and tutorial documents on the web. Okay, let me just quickly repeat this process for some other elements like transistors and diodes. So let's begin with a transistor, an NMOS transistor. I need to make a new schematic and do the same process for an NMOS transistor. So I want to do a basic DC simulation with an integrated NMOS transistor in a 0.18 micrometer technology. First, let me bring the generic symbol for an NMOS transistor. I need to click on the component and find NMOS 4, which is right here. Hit OK and place it in the schematic. Let me first complete the circuit. I want to perform a DC characterization by applying a DC voltage to the gate and another DC voltage to the drain of the transistor. So I need 2 DC sources. Again, we have to go to the component and find voltage. Hit OK. Then I need to do the wiring. I'm connecting the positive terminal of the sources to gate and the drain. And don't forget to place the ground of your circuit. So I'm going to connect the source of my transistor to ground and also the negative terminals of my voltage sources. The fourth terminal of this device is connected to the bulk of the transistor. So you can also simply connect this terminal to the source of your transistor. Now it's time to add the model of the transistor. The model I'm using here is BSEAM 0.18 micrometer technology, available on this website, and if you go down, you can download it from here. So I have already downloaded this text file, and if you open it, you can see the value of different parameters to solve the MOSFET equations. For example, here you can see the nominal value of the threshold voltage of this device. Let's copy the whole text and paste it into the SPICE directive right here. Hit OK and place it in your schematic. Now you need to assign this model to the transistor. Before that, just take a look at the name of this device, which is NMOS. So if you right click on the symbol, you see the model name, which is exactly the same as the model name of the transistor. You don't need to change it, and but you need to assign the length and width of the NMOS transistor. Let's assign the length to a bit longer value than the minimum, say 200 micrometer, and also give 400 micrometer to the width value. Click on OK. We also need to give the values to the DC sources. We haven't assigned anything. So the nominal supply voltage for this technology is 1.8 volt. So I'm going to measure the current flowing through the transistor due to that voltage. So I put 1.8, and I also need to change this value. I'm choosing 1 volt for the gate voltage. Click on OK. Now we have to set up the simulation type. I want to perform a DC operating point analysis, and click on the operating point and paste it on your schematic. Now run the simulation. Here you can see the result of the simulation. Specifically, if you take a look at the current of the transistor, you see that you have about 74 microamp flowing through the transistor. And also, if you close this window, you will see another file giving the large and small signal parameters of the transistor. This process is quite similar for a diode. Let me just quickly mention the way you select a diode model available in the library. Here you can find the diode symbol, click on it, and place it in the schematic. If you right click on it, you can pick a new diode and select your desired model. For example, 1N4148 is the well-known, most frequently used diode. So you can select that one and then draw your schematic and perform your simulations. Yes, so yeah, thank you for your attention. I hope this short video has been useful for you.